Welcome to AP Physics Made Easy. My name is Eric Sampson, and what I want to do is get you a 5 on your AP Physics test. So let's go ahead and learn ourselves some physics. How about it? In today's episode, we're going to be looking at how to use basic trig functions to solve two-dimensional kinematics problems. Sounds more difficult than it is, so let's just jump in and get to it. So you're going to find that in AP Physics, it's often necessary to use basic trigonometry, sine, cosine, tangent, in order to solve problems, mostly in kinematics, but also with forces and momentum, as we cover that later in the year. But the thing is, you really just need these basic ones. So hopefully you remember SOHCAHTOA from math class. If not, if you remember, this just means sine equals opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And if you can remember SOHCAHTOA, which you probably do, that's really all you need. So let's just see how we're going to apply this. So we're often told, at least in two-dimensional kinematics problems, that an object is launched at speed v at angle theta. All right, and so we've got to use that to determine the various aspects of its motion, how long it's going to be in the air, how far it's going to go horizontally, and so on. So the trick here is to take this information here and use these trig functions to establish the component velocity vectors. I know it was launched at this speed, but that doesn't really help me. I need to know the vertical speed and the horizontal speed in order to solve these problems. So to find the vertical component, I'm going to use sine theta. So I'm going to say v times sine theta is going to tell me this vertical component. And this works because sine theta is opposite the angle. Now let's go ahead and try to use this for the horizontal component. It's the same idea, except in this case, it's the adjacent. So the horizontal velocity component is adjacent to angle theta, so therefore I'm going to use cosine theta to find it. So you get problems like this in AP Physics a bit. So we say when a projectile is launched at velocity v at angle theta above the horizontal, it lands distance d away. Let's just see. So it lands distance d away here. How far would it land if it was launched at 2v? It's a pretty typical kind of question you might get asked. So how do we go about solving this? So the first thing we got to keep in mind is, since it's the vertical component of velocity that's going to keep an object in the air in one of these up-down problems, then if it's traveling at speed v sine theta upwards, if I double the speed to 2v, then this becomes 2v sine theta, which means it's going to be in the air twice as long, right? Because if it's going up twice as fast, it's going to be in the air twice as long. You might want to look back at the video I did on two-dimensional kinematics in the episode before this if you've forgotten. Now, if I think about the horizontal, it's also going to be doubled, because if I double v here, then I'm doubling this from v cosine theta to 2v cosine theta. So it's traveling twice as fast horizontally. So it's traveling twice as fast horizontally, and it's in the air twice as long. So therefore, it's not going to go twice far. It's going to go 4 times as far. But let's see mathematically why this is true. So if we were asked to write an expression for how far the object would travel horizontally if it was launched at speed v and angle theta, let's go about doing this mathematically, okay? So again, this goes back to the episode I covered just before this. So the first thing I want to do is I want to find how long it's in the air, and to do that I need the vertical component here, and the vertical component can be used in this equation here, because the time in the air in these up-down problems, we're basically using a equals delta v over t. And if you recall from before, since it goes up for the same amount of time that it comes down, then I can just double v and say that the time is equal to 2v divided by a. Again, look at my previous episode if you're confused by this. And therefore, I have to keep in mind that in this case, though, I don't use v, I have to use v sine theta. It's not this one that's keeping me in the air, it's this one that's keeping me in the air. So I have to substitute v here with v sine theta. So this is going to tell me how long the object's in the air. It's going to go up for v sine theta over g and come down for v sine theta over g. So it's in the air for 2v sine theta over g. So now I know how long it's in the air. Great. Now I want to express the horizontal distance it's going to travel. Now keep in mind, it's not going to accelerate horizontally. That's one of the key ideas about two-dimensional kinematics. And this is the one equation that you can use for things that are not accelerating. Now I'm just going to rearrange this to solve it for delta x, so I get this. Now again, I have to keep in mind, this is not the horizontal velocity. this is. So what I have to do is I have to then say, well, v cosine theta is what I'm interested in because that's the adjacent, which is going to give me the horizontal. So I have to substitute this for this, giving me this. Okay. So now I know this is the equation I'm going to use to solve for how far it's going to go. But I'm going to substitute delta t with this because I now know what delta t is equal to from the vertical component. So let's just put these two together. I'm just going to substitute delta t into the expression and I get this. I'm going to go ahead and multiply this through. This is just too messy, and we'll see something important that happens when we do this. I have v here and I have v here. So when I multiply through, I get v squared. So on the AP test, if you were to simply write delta x equals 2v squared cosine theta sine theta over g, full marks, you get your 5 on the AP test. Good job. Thanks for watching my videos. But it turns out we could make this a little bit more beautiful. And again, this is not something you have to know in AP Physics. All the trigonometry that you need to know in AP Physics is actually on your equation sheet. So if you just flip it over, you'll see. And this is not on here, but this is kind of cool. This is called the double angle theorem. Talk to your math teacher about why it works, but the bottom line is this. If you say 2 sine theta cosine theta, it turns out that's equal to sine 2 theta. Again, not time for that in this, just talk to your math teacher about it. So let's go ahead and take this and then use the double angle theorem to come up with the range equation. So this is basically what we call the range equation. This tells you how far an object is going to travel horizontally across level ground. We should make that stipulation. If it's shot at a certain launch velocity at a certain angle theta. All right. So what can we do with this range equation? Well, let's try something here. We can see that the distance traveled is proportional to v squared. Right. I can extract that from here. So their proportional reasoning tells me that. Well, if I double the velocity, look what happens. It goes 4 times farther, which is what we just said before. All right? So mathematically, this is why it's true. We could do it logically using just twice as long in the air, going twice as fast horizontally. Well, because of this range equation, we're going to find that the angle is going to have a lot to do with how far the object is going to travel. So what we find is if I increase the launch angle, then the vertical component of velocity is going to increase, so the object is in there longer. However, the horizontal component is going to decrease, meaning it's not traveling as fast horizontally in that time that it's in the air. And these two factors work together to determine the distance. So let's just take a look at this. Let's just say I shoot an object at 30 degrees. So it follows this trajectory here. Now, if I increase the angle from 30 to 40 degrees, I see it goes further. Now, at 40 degrees, it has less horizontal component velocity, but it has a greater vertical component. So it's in the air longer, but going slower horizontally. Still, that extra time in the air is more of a factor, and it goes further. And if I increase a little bit more, I go to 45, I see that it goes even further still. Now, what this tells us then is between 0 and 45 degrees, increasing the angle is going to result in a greater distance traveled, at least across horizontal terrain, which is almost always what you're, no, not even almost always what you're given in AP Physics. But then what happens if I go a little bit further? So if I bring it up to say 60 degrees, what I find is it's in the air much longer, but it's going so much slower horizontally that at extra time just doesn't get it very far. And if I increase it even closer to 90, say to 80 degrees, most of its velocity is vertical. Very little of it is horizontal, so it just doesn't travel as far. So we find it is between 45 and 90, increase the angle results in less distance, and the one that sends it the furthest, as you probably already knew, is 45 degrees. Well, now, why does 45 degrees send the projectile the furthest? Well, let's just take a look at it this way. Here's our range equation that we worked out before, and we can see that delta x, the distance traveled horizontally, is proportional to sine 2 theta. So let's just put in a few angles here, okay? So that means then that the distance traveled horizontally is proportional to sine 2 theta. So I'm going to make a column of angle versus sine 2 theta. So I have 20 degrees. It's going to go, I get a value of 0.64. So basically I'm going to multiply this by 0.64 to find out how far it goes. If I increase it to 30, I get 0.86. Now notice, this is bigger than this, so if I multiply this here by a larger value, it's going to go further. If I increase it to 40, it gets even bigger. Now watch what happens when I get to 45. You can probably already figure it out. Yep, I get 1. All right, so basically when I get to 45, I basically have v squared over g is how far it's going to go. Now, if I go beyond 45 degrees, and I'll just do it one time, I go to 46 degrees, you'll see I'm already getting smaller. So that's why 45 is the most. You'd never have to get this far into the weeds on the AP Physics test, but I do think it's interesting. If two launch angles add up to 90 degrees, and they do like to ask this, then they'll both send the projectile the same distance horizontally, and we call these complementary launch angles. So let's just look at an example of this. So let's just say I launch something at 20 degrees. It has a lot of horizontal velocity. It doesn't have much vertical velocity, but this is how far it travels. Well, what would its complementary angle be? Well, I just say 90 minus 20, that gives me 70. So at 70 degrees, if I shoot it at that angle at the same velocity, it's going to travel the same distance. So for every horizontal distance traveled, there's two angles that will get us there with the same launch velocity. Let's try doing it for 30 degrees. I shoot it at 30 degrees, it lands here. So I say, 30 minus 90, that's 60. So if I shoot at 60 degrees, it'll go the same distance. Well, let's explain why complementary angles produce the same distance using the range equation. Okay, so we're going to go back to what we had before. We said that, remember, the angle is basically the horizontal distance, rather, is proportional to sine 2 theta. So let's just take the angle and compare it to sine 2 theta and see what we get. All right. So at 20 degrees, we get 0.64. At 70 degrees, we also get 0.64. So if I take these two angles, plug them into here, this component of them yields the same value here. So you see the same is going to happen with 30. So at 30 degrees, I get 0.86. It goes further, right? And if I do it at 60, I'll also get 0.86. When a projectile is launched at an upward angle, let's just say here, okay, I've got 20 degrees vertical component and 20 degrees horizontal component. What you got to keep in mind is that the horizontal component is going to stay unchanged and the vertical velocity is going to go down by 10 meters per second each second it's in the air. So I launch it at 20 up and 20 horizontal. The horizontal never changes, but with each passing second, I'm going to, because have an acceleration, gravitational acceleration of 10 meters per second squared, after 1 second, 20 is going to be reduced to 10. Another second later, 10 is going to be reduced to 0. So I don't have any vertical component here. This is the apex of the launch, and it's really important to keep this in mind. At the apex of the launch, the object is still moving. Right? Its velocity hasn't gone to 0. Its vertical velocity has gone to 0, but it still retains its horizontal velocity. So one way we can find the horizontal velocity is when we look at a graph, we know that at the apex, all the velocity it has is its horizontal velocity that it had initially. I look at a second later, again, I still have 20 horizontally, but now I've got 10 in the negative direction, followed by 20 in the negative direction. Now, let's look at what would happen if I produced a speed versus time graph. And they do like to ask these. So keep in mind, speed is a scalar. It's not a vector. We're just saying, like, what is the magnitude of your velocity vector over time based on your launch? Okay, so if I launch it at 30 horizontally and 40 upwards, let's just see what we'd get. So let's start off, let's figure out what our launch velocity was. Well, how are we going to do that? We're going to use Pythagorean Theorem. So we're going to say 40 squared plus 30 squared, take the square root, I get 50 meters per second. So I'm going to put a dot here at 50 meters per second. Now what's going to happen is, a second later, this will be the same, but this will be reduced from 40 down to 30. So I'll put that into here, and when I solve this, I get 42. Its velocity has slowed down. Well, I should say its speed is now lower. Okay, its magnitude of its velocity is as well, but so I have 42. Now let's say another second goes by, so 30 will become 20. And now I get 36. Let's put a dot at 36. I'm going somewhere with this, bear with me. A second later, it's 10. So now when I do this, notice this one never changed. It's always 30 squared. So now I get this. And finally, this goes to 0. And I get 30, which was my launch velocity. But now watch what happens. A second later, it's going negative 10. But what we find is negative 10 squared is the same thing as 10 squared, so I get the same value here. So if I look over here, what's going to happen is it's going to start coming up now. And if I just kept doing this for each of these seconds, I'd get this graph here. Now the thing is, when you look at these speed versus time graphs, you have this curve, and you can tell that this right here is the horizontal velocity, where the minima here is, this is what its horizontal velocity was. And at time 0, that's the launch velocity. That's how you're going to approach these problems. So on the AP test, you often get presented with graphs like this. So a speed versus time graph, and asked to make some interpretations about the launch angle or distance travel, whatever, based on that. Okay, so how do we go about doing this? So first of all, how could I extract from this graph here the horizontal velocity? Well, the horizontal velocity is basically going to be the minimum speed that it ever achieves, because at its apex, it had no vertical velocity. It only had horizontal velocity. And I can see that that was 50 meters per second. So I'm going to come over here, and that's my projectile. I'm just going to draw 50 meters per second there. How about its launch velocity? Well, the launch velocity was its velocity at, its speed at time t equals 0, which is right here. So I know that the launch speed was 80. So I'm going to go ahead here and put 80 at that angle here. There. Now, if I want to find the vertical velocity, there's different ways I could do it, but what I'm going to do here is I'm going to use Pythagorean Theorem, because right now I don't know what this angle is. So the easiest way to do is use Pythagorean Theorem. And so if I do that, I would just say that 80, which is the hypotenuse, is equal to 50 squared plus x squared, and then take the square root. And if I just solve this, then for y, I'm going to come up with 62.4. All right, so now I know that this is 62.4. So if I want to find the launch angle, what I can do then is I can say, well, this angle is equal to this times the cosine of the angle is equal to this. So 80 cosine theta equals 50. So if I solve that for theta, I'll get 51.3 degrees. So you can see we can extract an awful lot of information out of here. And really, if you think about it, people, all we're having to do as far as the math of this is sine, cosine. We haven't even done tangent yet, but we're going to sometimes use tangent. And use Pythagorean Theorem. It's really not that challenging. All right, and I'm going to finish off with this. So let's just keep this in mind. If the vertical velocity, the vertical component of velocity is greater than the horizontal component, so if this is greater than this, well, the angle has to be greater than 45. If the vertical velocity is smaller than the horizontal velocity, well, then I know that the angle is less than 45. And if they're both the same, then I know the angle is 45. As always, thanks for watching. If you like this video, remember, like this video. Consider leaving me a comment. If there's some video you'd like me to make, I'd be happy to do that, or maybe you could just give me some feedback on how to improve. You might want to check the description below to see if there's some links I've included that could help you out. And of course, as always, I would really appreciate it if you would like and subscribe.